started. There's we're about 15 people in the room right now. So as I mentioned in the other room, my name is Caleb McDonald. I'm an application specialist for Mettler-Toledo. And so what we're going to be talking about today is trying to understand a safer thermal runaway. So looking at using evolved gas analysis. So taking something in the lab, heating it up, and seeing what's coming off of it and how much. So we obviously want to avoid thermal runaway if we can. The picture we have here on the front slide, though, is actually, unfortunately, from the LA wildfires that happened recently. So I wanted to put this into perspective because no matter how much we do to try to make a better and safer battery, there's things that are going to be out of our control, right? So we can't always stop nature. We can't stop car accidents. We can't stop other things that may spark a fire. And so we want to understand, even if we do everything right, and there is a thermal runaway, how do we make sure that it's safe for the people around? So this is actually the headline from that picture on the previous slide about crews tackling what was left after the fires occurred. So as I mentioned, there's been a lot that's happened to make a safer battery, but there's just things that are out of our control. And so we want to make sure that no matter what's happening, we want to make sure that what's coming off is going to be safe for the bystanders, for first responders, and everyone involved. So how can we do that in a lab? In the lab, we can actually go through and we can test materials by doing evolved gas analysis. So what is evolved gas analysis? It's where we take a TGA, which is right here. Let's see if I can get a pointer on the screen. So we can take what's called a TGA, or a thermogravimetric analysis instrument, and we can couple that to some other gas analyzer at the end. And what we're specifically talking about here is using something called a micro GC with a mass spec attached to it. And we're going to talk about why we would use that and what we're actually going to be able to see come off of a battery. So what is a TGA? So in the simplest form, a TGA is essentially just a balance attached to a furnace. So we're going to heat something up. So if we look at this figure here, we have temperature on the x-axis and we have mass on the y-axis. So all we're doing is we're going to take a material, we put it in the instrument, we heat it up, and then we try to see what's coming off of the material. So what's lost. So there can be a lot of things that will be coming off. And we can start to see. However, this alone doesn't tell us what is coming. It doesn't tell us how much. It doesn't tell us at what so we can see that there's how much is coming off. We can't quite figure out what that is until the next minute. Hear me now.
Hey, Caleb, I think it's the noise outside is drowning you out a little bit. So whenever that noise gets louder, we can't hear you.
Oh, so that's why I put on the headphones. Hopefully, I was hoping the microphone would help. I'm putting the microphone closer to me. Is that helping?
Yeah, I can hear you a little bit better now, but I think it's also because whatever the sound was outside has maybe gone away or gotten a little bit quieter.
People came to mow just at the wrong time.
Of course.
So yeah, so we're looking at trying to see what's going to happen when we decompose a material. So how would we do that in the instrument? So this is a picture of a TGA. So this is what a furnace would look like. So essentially you're going to put a sample on a sample arm, and this sample arm is attached to a balance. And there's a gas that will flow across here. And so what will happen is, as we heat the material up, we'll see how much the mass changes on the right-hand side here. But then there's a gas flow that runs across, and it'll pick up whatever's coming off of the sample, and that will come out the outlet of the instrument. And at that outlet is where we could actually put some kind of gas detection device onto the instrument. So we can see here that this is kind of a picture like we saw a couple slides ago, that we can see that there are mass losses, but we don't know what they are. So what is coming off? At the very beginning, it could be water, it could be some kind of organic solvent, it could be oil, we don't really know. And then we know when it's decomposing, we can't really tell what is coming off of we can't tell what's coming off, we can only tell how much. So the next thing we can do is we can put a detector on the end of the TGA to try to pick up what is coming off. And there's different detectors we can put on the end of the instrument that can give us different types of information. So we can actually put on either an FTIR, so a Fourier transform infrared spectrometer, so we can do IR spectroscopy on what's coming out of the instrument on the end of the TGA. A lot of times that's the easiest to do some analysis on. We can put a mass spec directly on the end of the instrument, or we could put either a GC mass spec on the end or a micro GC mass spec. Now, there's different reasons to put different types of detectors on the end of the TGA. The simplest are an FTIR or a mass spec, but the problem there is everything that's coming out of the TGA goes into there at once. And so if we look at something like this, if we have one big step where things come off, all of this will go through into your FTIR or your mass spec at once. And then we can't really we can have some issues resolving what's coming out. If we use a micro GC or a GCMS, we can actually, when those gases come out in one big step, we can actually go through and then further separate them using either with the GCMS, a single GC column, or a micro GCMS, we can actually have three small individual columns that can then go and separate the materials out. So these are different things that different advantages and disadvantages for the different types of systems. The most common that we end up using for battery materials are going to usually be the TGA with the FTIR or the TGA with the micro GCMS attached to it. The IR works really well if I'm trying to pick up things like HF, if I want to understand if I have that coming out, which is a gas that we would be worried about. But the micro GC works really well for a lot of the other compounds that we're looking for, like say hydrogen cyanide, cyanogens, things of that nature. So if I'm trying to separate out some of these materials that could be coming off in one big chunk out of a decomposition, you can see that if I want to pick between the TGA with the micro GC or the TGA with the GCMS, the full one, the different compounds would give us an idea. So if I'm looking for heavier compounds, the full GC would be better. But if I'm looking for lighter compounds, the micro GC is better. I can actually have more separation, and it's going to be faster. When we're looking at what's coming out of a lot of these battery materials, especially cathode materials and things of that nature, we're not looking at a lot of these big heavy compounds. We're not looking at large hydrocarbon chains. So the micro GC is kind of the thing that we use the most often. So what is a micro GC? I mentioned that we would put this on the end of the instrument, but what is it and how does it work? So a micro GC is actually an instrument where we're going to have a carrier gas come through, and we're going to take the sample gas from the end of the TGA. It's going to get injected through a manifold, and it's going to get split through three different columns, and then that's going to go into an MS. And you have a TCD detector and an MS at the end. So we can actually separate out these gases and separate it through three different types of columns at once. So what we have is we can actually have three different modules. You can have module A, module B, module C. Each of them can have different specificities to be able to separate out different types of gases. And then at the end, we can actually have a mass spec attached to it. So this is just an example of a TGA mass loss curve. So we can see that we're having our sample decompose. And this curve, this purple one, is just the first derivative of that curve. And so if we look here, we can see that if we look at what's coming out of one of these modules, you can actually pick up the signal of these materials as they're separated out. So why would we specifically do this with battery materials? So one good example is looking at a black cathode powder. So this was just a cathode powder that came into the lab. And you can see if we put it into the TGA, we get a lot of steps of mass loss. So you can see there's an early on step that's around 100 degrees. So this is probably going to be a volatile of some kind, a volatile or water. And then we start to get into the decomposition of the material. And you can see it's very complicated. So if I look at the first derivative is essentially telling me the rate of change of this curve. It helps you to better visualize what might be, where there might be a mass loss step. And you can see it's extremely complicated. So by just looking at the TGA curve, I can't necessarily say exactly what's coming off, but I can get an idea of how much mass these different steps possibly could be. Now, the next thing we can do is we take this material here, and it's going to go through that micro GC that I mentioned. So if we take that and we connect it to the micro GC, we can now see we have different columns. So you have module A and module B, and we can see what is actually coming out of these modules. And so this is a table of the different temperatures, and you can see at the different temperatures we have mass losses of, say, at low level 2%, then 9%, and then all the way up that the final residue is 75%. Now, if we look at what's coming off in module A versus module B, we can see that we're picking up some hydrogen and nitrogen and just some CO. So in module A, it's pretty innocuous. There's nothing I would be too worried about. But if we now look at module B, we can see that we have CO2, but we're also picking up some cyanogen and some hydrogen cyanide. And so these are two things that we would definitely be fairly worried about coming off in a thermal runaway type of event. We would not want to be having cyanide or a cyanogen coming off. Now we can further confirm, so here, this is just done by retention time on the column. So this is just understanding if we put the material in, how long it's retained on that column. However, we can also connect the mass spec at the end of that micro GC, and we can very specifically pick up the masses of cyanide and cyanogen out of this material. So we can very accurately detect that these are in that that they were when we're going through a decomposition, that these are coming out. So where do they come out? So now we can kind of overlay everything that we see from the TGA with the micro GC. So we can see again, this was our mass loss curve and our first derivative, and it's very complicated. But we can then take and get the actual traces of each of the evolved compounds that went through the micro GC and see where they actually arose temperature-wise. So we can see that if we were to quantify, we get a lot of hydrogen cyanide coming out of the material starting around 300 degrees, and it carries all the way through kind of to the end. And then if we look at our cyanogen, that's coming out around a similar temperature range. So we can see if the material, it stays below 250 C, we don't have the evolution of these really toxic compounds. But if we actually go through a thermal runaway and have a fire, we do have to worry about hydrogen cyanide coming out of this material. So in kind of conclusion of what we have here, hydrogen cyanide and cyanogens they're really reactive. They're very toxic compounds. We want to avoid having these come out in a battery thermal runaway type of situation. We can see that with the TGA with the micro GCMS attached to the end of it, we can very easily pick up the hydrogen cyanide and the cyanogen in the decomposition process. So we can easily see that they're there, and we know that they're there. Now, where did they come from? That's the next question. In a cathode material, we may not necessarily expect to be seeing hydrogen cyanide and cyanogens coming off. Well, the presence of cyanide and cyanogens is suggesting to us that there was some type of contaminant in the cathode material, some type of foreign substance that wasn't supposed to be there. So this is a great indication of not only is this going to be, if this is left alone, that this is going to be dangerous if there was a thermal runaway. This is also giving us information that there's a contaminant in our cathode that could shorten the life of the cathode as well, and maybe the efficiency of it. So we see this in the lab scale, can tell us to go back and look at the cathode and go, okay, we might need to be doing something to try to figure out where this contamination is and pull it out of our production. So knowing the presence of these contaminants is not only going to help in the event of an unfortunate thermal runaway type of event, but it's also going to really help to give us a better performing battery overall. So there are a lot of different types of evolved gas analysis. So if you wanted to know more information on evolved gas analysis in general, Mettler actually has a full EGA handbook. So it can kind of go through mass spec, FTIR, micro GC, and there's also, we have a lot of different user comms and application notes on it. These are actually all free. So you could go right on the Mettler website, download them, things of that nature if you wanted to see them. And so with that, I just want to say thank you. We can kind of, if you have any questions or start a discussion on it, and this is just a picture of that unit like we saw earlier on. So now you actually can see this is the TGA, this is your micro GC with 3 different columns, and then this is the mass spec attached to the end of it. So with that, I'll open the floor to any questions, anything you would like to know more about, any concerns, things of that nature, and kind of go from there.
Hi, Caleb. I have a question.
Yes.
I was wondering with what frequency you can resolve the gas analysis. So I saw something about 1 to 3 minutes. Yeah.
So what's happening with the TGA is so that there's different types, depending on what's on the end of it, that can give us an idea of the kind of the retention time and the resolution. With the micro GC, what's happening is there's 3 columns inside here, and these columns are very small. So they have roughly about a 1 to 3 minute retention time on the column. So this is considered to be a pseudo-online, what we would call a pseudo-online technique. If I were to connect a mass spectrometer directly to the end of the TGA without this in between, the mass spec would immediately pick up everything that comes off the end of the TGA. But with the micro GC in between here, the columns give us about a 1 to 3 minute delay. Now that's a known delay, so we don't have when we go to overlay the temperature with the retention time data. So if we come back to this will all overlay properly because we know what that delay is in the columns, but the column will have some delay to it. Now, if I was using a full GC on the end of the TGA, that would have a very long delay, so we would have to make small injections. We couldn't just take all of the gases and put them directly into the end of the instrument. So, but this would actually make it so that we don't have to worry about any resolution issues. There's just a slight delay.
Okay, thank you.
Okay, I have a question. It says, I would like to know where you are influencing the code cycles to conduct these tests and provide the data to the AHJs. Could you further elaborate? I don't really know what you mean by influencing the code cycles in terms of that.
So Caleb, thanks for taking my question. I come at this from a completely different kind of purview than everybody else. I'm not from the manufacturing side. I'm representing manufacturers of batteries in municipalities. I'm specifically out of the San Francisco Bay Area, and I meet with firefighters regularly. And one of the big blockers to local municipalities having batteries is the firefighters. They can pretty much interject to just stop a battery from being put in a building. And some of that is just fear and lack of information as to what the compounds are that are in battery fires and what the firefighters are facing. And in that unknown, they're just saying no, right? That's the easiest answer to come up with. I mean, my very specific question would be, we have here in San Francisco and throughout California, the UL 9520 standard, and it's basically effectively useless for giving people the authority to say yes to projects. And, you know, a lot of the manufacturers are looking
Oh, I think I may have lost you there for a second.
for something by yet, and you're like, did I lose you guys completely? Am I back?
Yeah, you're back now. Yeah.
So how much of that question did you get?
Yeah. So I got to the part where you're talking about the firefighters blocking the at municipality levels, and you're going into the UL standard. I think I know where you're going with it now. That so unfortunately, what we've been doing right now is the testing we do is all of this was done for customers to buy a system. When the systems have been purchased, they're usually right now the data for it is all on the R&D side. We have them at different battery manufacturers, some auto manufacturers, and they do this. They're doing testing like this on the R&D side to try to look at the compounds that they're working with. But unfortunately, there's nothing at the moment where anybody takes this data and is either showing it as very publicly or is using it in any type of code to show that, hey, we should be showing what is coming off of the batteries. And I think we definitely should be. I wish that, you know, in order to get something to market, if everybody had to test it in this fashion and you would know exactly what compounds are coming off and how much, it could give some people more of a peace of mind. I know for sure, like where I'm at, I'm located in North Carolina, just about 3 miles or so from where the new Toyota mega site is. And there's a lot of people, because this area is very rural, there's a lot of people that when they started breaking ground here, a lot of farmers were terrified because they just had no idea. They don't understand batteries. They don't understand the process of making them and their safety. And they thought that the plant was going to kill their cows and things of that nature. So the more of this information we could get out into the public would be fantastic. So I would love to be able to have some kind of something in the code that would say, hey, you know, you have to test this, and it would show exactly what's coming off and how much.
It's me, Sophie, again. I would have another question. Yeah, I would like to know, with your system, is it possible to also quantify the amount of gas that is evolved? So like, for example, how many milligrams of CO, for example?
Absolutely. So it can actually, this can all be quantified actually. So at next week at the battery show in Atlanta, I'm going to be giving a little, I didn't know how technical our audience was going to be today. So I didn't want to go into too much crazy depth on exactly how to do like quantification and things of that nature. But we absolutely can quantify what's coming off. I'm giving a talk at the Tech Forum at the battery show in Atlanta next week. And there I'll be going into all the depth of exactly how to quantify, like say how much of this water is coming out of the compound. So we can absolutely do that. It takes a little bit of effort, but you can absolutely quantify exactly how much of each compound is coming out.
Great, thank you.
Any other questions? All right. Well, I guess if there are any other questions, I'll just thank everybody for your time for being here, and hope to see some of you, possibly anybody who's going to be in Atlanta next week. And if not, hopefully connect at the next forum next month.